Okay, and we are back. So we are in sections 3.1 to 3.4. We're looking at that normal stress and strain, and this is example number 2. Okay, so we have a rigid bar DA, or the bar DA is rigid and is originally held in the horizontal position when weight W is supported from C. If the weight causes B to be displaced downward 0.025 inches, determine the strain in wires DE and BC. Also, if the wires are made of A36 steel and have a cross-sectional area of 0.002 inches squared, determine the weight. Okay, so when we have something like this, we have to just remember, we know that stress is P over A. That's the internal. We know that stress equals E times strain, and we know that strain is change in length over original length. So this is all we have right now. We have these three equations, okay? So we have a rigid bar. That's important because when I load it, it is going to rotate with rigid body rotation. We're not going to see deformation in that bar. So it's just a perfect little rotation there. When we put weight here, if the weight causes B to be displaced downward, determine the strain in wires DE and BC. If the wires are made of A36 steel, determine what that weight is. So we're at a point now where we're going to have several free body diagrams, and I call the first one statics or equilibrium, and it's kind of like how the forces are being distributed within my system. So I have this bar, and I need to remember that at A, I actually have a pin there, so I have to have AX and AY. And then I'm going to have that force in cable BC that's pulling down. I have 3 feet, 2 more feet, and then I'm going to have the force in DE. Okay? And I'm going to remember that that force that's pulling up, okay, so when we cut it, it's pulling down here and it's pulling up here, that the force in BC is equal to the weight that we're applying, okay? So if I wanted to come over here, if I'm taking my scissors and I'm cutting it right there, there's going down, here's going up. Force BC. So I can sum forces in the y direction here, and I'm going to find that the force in BC is equal to the W, okay? Now we need to have a relationship between BC and DE, so we're going to sum moments about A. And I'm going to get that 3 times the force in BC minus 5 times the force in DE equals 0. Okay, and when I do that, we can simplify, and I can find that the force in BC equals 3/5 W, or I could write it the other way, that the weight is 5/3 force BC. And then we also want to remember that we are also going to be looking at how that weight affects both BC. Why do I have BC in here twice? This should be DE. Because I changed it. Let's go DE. This is DE. And I changed that force of BC was actually equal to W. So now we have everything in terms of W. Okay. Now we're going to have a free body diagram. And this is what I call deformation. What is the relationship between applying a load and what happens to my system? So I can see that I'm starting out, I'm going to have that nice rigid bar rotation. So it's going to rotate, and I'm 3 feet, 2 feet. So this is going to be, I'm going to go from a D to a D prime. So this is the change in length of that cable DE. And this right here, we go from B to B prime. And this is actually that change in length then of from B to B prime. But we're not actually changing a cable length there, we're just rotating down. And I know then that the change in length of cable DE is to 5, as B to B prime is to 3. And we were given that B rotates down 0.025 inches, and then we are to 3. Okay, so using our deformation, and using similar triangles, I can now determine, that delta DE equals 0.04167 inches. Okay, it's just similar triangles. And if you look at this, you're going to see you have one triangle right here because that rigid body rotation. Okay, that rigid body rotation. And then we see that slope, it's the same slope as we go to this bigger triangle. Okay, so 3 is to B prime as 5 is D to D prime. Okay. So there's that. So now I know that the change in length of cable DE is 0.04167. Okay. And if I know that, then we can start figuring out, well, what is the actual weight that causes the displacement at B to B prime, which causes the displacement here, which is really the stretch in that cable. And so if I'm looking at cable ED, okay, stress equals E times strain. And stress is, that internal force of cable ED divided by the area of ED. Okay, strain is a change in length of ED divided by the original length. And then E is a material property. We are told that we are using a 36 steel, so E is 29,000 KSI. Okay, so now we can actually solve for that internal normal force that occurs because everything else is given. So I have internal normal force from E to D divided by that cross-sectional area of 0.002 inches squared equals 29,000 KSI times change in length, 0.04167 inches, is to, now there's a lot of things going on over here. Here is my original length. Okay, it's that, so it's 36 inches. Okay, and when I work this out, I get that internal normal force of cable ED is 67.1 pounds. Okay, and now I can go back and use my statics, and that tells me that my weight is 5/3 normal force, is 5/3 of 67.1. So the weight that causes that rotation is 111.9 pounds. Okay, so now that we have that, it says determine the strain in the wires. Well, let's determine strain. Let's look at cable DE. Okay, so strain equals change in length over length. Well, we already have that change in length, 0.04167 divided by the original length. Okay, and so we can find that strain of ED equals 0.001158 inches per inch. What we have to be sure to check is that we haven't yielded. Okay, we have to make sure we haven't yielded because these equations, when I look at these equations, these equations are assuming that we are in that elastic region of our curve. We are assuming that the stress is 36 KSI or less. This is the yield stress for a 36 steel. It's 36 KSI. So when I use this modulus of elasticity, look at that. That is only valid in that elastic region. Okay, so I need to make sure that we are actually within the elastic region. So let's check that stress of E to D, and that's going to be the normal force that we had divided by the area. The normal force was 67.1 pounds divided by that cross-sectional area, 0.002 inches squared. And when I divide this out, I'm going to find that it is indeed less than 36 KSI. So this is indeed less than yield of 36 KSI. So far, everything we have is valid, and this is correct. Now, when I go to find cable BC, okay, I know that we have stress equals E times strain. And if I know the stress, that's just that internal normal force from B to C over area of B to C, which this was our weight, okay, 111.9 divided by, and our area is 0.002. So now when I calculate that stress from B to C, and I take 111.9 pounds divided by 0.002 inches squared, I get a stress of 55.9 KSI. That is greater than yield of 36 KSI. Okay, that is greater than yield. So I cannot use this equation because this, remember, E is only valid in, okay, this equation right here, valid in the elastic region. So how do I find the strain then if I'm outside? Well, that's where I have to go back to an actual stress strain curve. And if my stress is 55.9, well, that's kind of like if I want to look on here, here's 50, here's 60, so 55.9 is going to be just above that midpoint. So I'm going to draw straight over, and then I am going to take this and kind of come straight down best I can. Okay, and what we have to remember is these bottom numbers are the elastic region, which I'm above 36 KSI, so I'm having to use the top numbers. I can see that this is 0.1, this is 0.2, so this has to be 0.15, and when I look at that value, it's about, I'm going to say 0.11, okay? So when I'm looking for that strain now, that strain of B to C, it's actually what I've read off of the chart, which is 0.11 inch per inch, okay? Which is much, much greater, okay? This is going to be much, much greater than the strain I would find if I took stress over E, okay? So that strain would be much, much smaller. When you look at solutions manuals, the solutions manual for this problem does not check yielding, okay? A lot of times on CHEG, they don't check yielding. But now that we understand stress equals E times strain is only valid in this elastic region, okay, we have to always check to make sure that our stress is less than that yield stress for that material. If it's greater, we have to go and use the chart method for strain.